But yeah, okay, now it's on.
Okay.
So
let me try to share my screen and tell me whether you see it.
Do that, and while yes, it works, and let me just give a short introduction. So welcome everyone to the seminar for finite geometries and groups. Today's speaker is Hetman from Lviv, Ukraine. And you can see the title already, Algorithms for Finding Steiner 2 Designs. Let me just say that I was very impressed with Ivan's constructions. He has very nice results about the new Steiner 2 designs, which were previously unknown. And some of them I've been trying to construct very hard myself. And so I obviously unsuccessfully, but Ivan managed to do it. And he is going to tell us something about these constructions of his and about the algorithm he used. So please, Ivan, do go on.
Okay. So let's start. Firstly, about me. I have a PhD in mathematics. 10 years ago, defended my PhD thesis about topological structure of hyperspace of closed convex subsets in linear topological spaces under the supervision of Taras Banach, who is present here. I was a PhD student at the Department of Geometry and Topology in Lviv, and historically our Lviv geometry and topology school has a lot of topology and almost no geometry. This has historical reasons, and still my PhD thesis was a little bit geometrical because I was considering convex subsets there. So after that, I went to IT for 10 years and did almost no mathematics. That were personal reasons, obviously the money. But when the war started in 2022, I decided to take a sabbatical and went to the university back and contacted Taras. And at this time, Taras wanted to learn and study geometry. And that was how the Lviv geometric seminar was established. And I always enjoyed geometry and was very happy to be an active participant of this seminar from the very beginning. And eventually, I found my personal area of study. It is Steiner 2 design. Okay, I think that we need to mute Alex because I hear some background noise. Yeah, okay. Now let's proceed. So little bit about history of our Lviv, I would even say geometric school. So our Lviv geometric school in the beginning was kind of isolated because we were just gathering knowledge in the beginning and reinventing the wheel. And you should also understand that in the beginning our seminar was kind of isolated. We did not have contacts to outside world. Yeah, this was how it was, and that it had default learning curve with internet with the only source. So during that time, Taras Banach started writing his book Linear Geometry and Algebra. He advertised this book in his Monday's talk. So you can download it and take a look about the terms and notions we are using there. And during that time, we have found that for every discovery you make, there is like 50 years old German paper in German language, which has exactly the same theorem and example. This was at the beginning very disappointing because you think that you found something, you cannot find it in English source, but unfortunately you find it in German sources. And this is, and from that time, we ended up with such definitions. Taras introduces the definitions on this talk, but let me shortly repeat them. So first of all, we have a notion of liner. Liner is a structure that consists of the set of points and family of lines that are satisfying two axioms. My axioms are a little bit different, just because I need them to illustrate better my example. So first of all, first axiom, it is exactly the first axiom of Euclid that through every two different points, there exists only one line that goes through that point. And second axiom, just to get rid of degenerate cases, I'm saying that every line should have at least 3 points. So these axioms still have a lot of different liner structures that are extensively studied in liner and incident geometry. So to restrict these structures a little bit, I'm adding one more notion. It is a two-balanced liner. So two-balanced liner, it's basically the liner where all lines have the same length. And as you can see, liner with these three properties, I mean two axioms and third property, it is exactly Steiner to design with Steiner to design and balanced incomplete block design with lambda equal to 1. So this is, how to say, my standpoint, how I am considering design. So I'm considering them initially not from the combinatorial, but from geometrical point of view. Okay, and because I'm considering them from geometric point of view, obviously I tried to find something similar to the common geometry in this finite liners. So simple definition that for x belong to x, we define the set of parallel lines. This is the lines for every point x and for every point line L. We consider the set of all lines that do not intersect the line L and pass through the point x. And obviously there are three cases as in the common geometry. So we can, using this notion, classify planes, and there are three cases. First of all, there are projective planes. It is planes where every two lines intersect. Second, it is affine plane. Affine plane, it is a plane which satisfies, as Taras told Playfair's axiom, that when we have a line and a point that don't belong to this line, there is exactly one parallel line that goes through this point. And third type, it is hyperbolic. It is when we have points that do not belong to this line, we have at least two lines that pass through this point and do not intersect the line. And all the examples of finite projective and finite affine planes, but the natural collision arises at this point. For me, it is obvious, but at that point, we didn't know whether the hyperbolic plane exists. So this was how to say, simple problem, but I was not able to find it in the different sources. So let's that basically moved us to the second stage of our findings. And during the second stage, we reinvented some wheels, we collected and gathered some knowledge, and started to determine the best knowledge sources and to reach boundaries of the discovered. And I would like to advertise also two books. I suppose that one book you should know about it. And second book, it is a very nice book, Thomas Q. Sibley, Thinking Geometrically. That is like undergraduate student book, but still it is written very well and contains a lot of things that for the student who would like to study the geometry. Okay, and at that point, more and more of questions appear. And it appears that often it is easier to verify effect computationally than to find it in the internet. So when you are looking through the internet, you need to understand that somebody's definition is something like you did. You need to adapt it, for instance, to units, and then understand that some example, which can be even avoided, corresponds to your definitions. And due to that fact, I started writing the code that just started testing some assumptions. And due to that, I need to have a database of finite geometries arrows. And then I advertised the book of Thomas Q. Sibley, and in this book there is very nice geometric inspired example of the hyperbolic plane. So you can build the hyperbolic plane very easily. So let's assume that you have 13 points, and you have two triangles. One triangle is with sides 2, 5, 6 in this cyclic structure, and second triangle has the lengths 1, 3, 4. And as you can see, these two triangles, they have I will call this differences between points completely different, and this difference cover all possible differences between points in this 13 points. And this is the first stage. And when you assume that this triangle, first triangle and second triangle are lines, and rotate them 13 times, in this case, you can see that the obtained structure will satisfy all properties that I mentioned about the balanced liners. So first of all, there for every two points there exists a unique line that goes through these points. This is obviously finite liner with no degenerate lines, so all lines are of length 3, and all lines are of length 3. So this is the smallest example of two balanced hyperbolic plane, and this question was answered. But this image contains very powerful idea, which actually is the base of all my algorithms. How strange it is. So, okay, I already told that two balanced liner is equivalent to Steiner to design, and to balance complete block design BBD. So after this, I realized that what Handbook of Combinatorial Designs is about. It is basically Handbook of Combinatorial Designs. It is basically about VVD with V, K, and lambda. But in my case, lambda is equal to 1. And also, yeah, this is a visualization, this image, of cyclic difference family. It has abbreviation CDF. It is also widely used. And I began to write an algorithm that generates this cyclic difference families. Because the cyclic difference families, it is a rich source of finite geometries. And using this rich source, you can actually have a database, which I mentioned in the previous slide. And using this database, you can actually verify some assumptions that were needed for Taras books or for my findings and so on. Okay. Let's go further. Then third stage began. So during this stage, first of all, Taras continued writing his book, and we kind of split our study. So Taras continue considering mostly affine and projective planes because they are the common object of finite geometries, and I started writing and improving an algorithm for finding CDFs, and generated a large database for producing examples included into Taras books, and also verify some my assumptions. And at the end of 2023, actually, I reached the bounds of CDF enumerations from handbook. Then I started looking for more results because I assumed that book was written in 2007, and I found a nice paper about from two Bulgarian scientists, Baichev and Topalova, and they extended this enumerations from the handbook. But when I was reviewing these enumerations, I found a small mistake in the paper. They calculated one number wrongly. I reached them via email, and after some conversation, actually they confirmed that my number was correct. And this was the first contact with outside world of our review geometric school. Eventually, I started improving my algorithm, and even found unknown cyclic unital of order 5 after 4-day search. Now the full search for cyclic unitals of order 5 takes only 10 minutes after the improvements of the algorithm. And I discussed it with colleagues who are present here, and started generalizing this algorithm. Okay, so before I will introduce my algorithm, let me firstly define the also very important structure. I suppose that the people who are writing computer programs are aware of it, but yeah, this is very important structure, and this structure allows a lot of memory improvement, performance improvement, and so on using the algorithms, and basically almost all sets that you will see in my algorithms, they are bit sets. Okay, so let's define this bit set formally. Bit set, it is, I did not write, unfortunately it's there, but bit set is basically a map from a specific subset of fixed domain to the 0 or 1. So it is characteristic function of a subset of some fixed domain that consists of numbers from 0 to v minus 1. And if v is less than equal than 64, current computer architecture, it is a current computer architecture, it is 64-bit machines, almost all, and then we can use 64-bit machine words to represent this bit set. And usually in this case, we have dramatic performance improvement due to this fact, because in this case, bit sets can be stored in registers instead of operative memory, and so on. And computer language variables in this slide corresponding to a specific sets will be denoted by corresponding lowercase letter. Okay, let's go further. So when you have bit sets, then you have logical equivalent for operations on the sets. So for symmetric difference, it is operation XOR on this set arrays of machine words. For a complement or logical operation not, you have just D XOR A, where D is the word that consists of only ones. For union, you have or. For intersection, you have and for complement of two arbitrary sets, you have a combination of two. It is A and not B that you can use. Also, due to the fact that bit sets are on the ordered are subsets of this domain that consists of integers, you can also do lexicographical order comparisons, like check whether A is less than B and A is less than equal than B. And also you can perform cyclic shifts, like you can add number or subtract number from the set modulo V. And computer implementations of this operation still are effective, but more complex. And for instance, a fast algorithm for cyclic shifts that is making only 1/16 of elementary operations of the number V was proposed by my friend Roman Obuchivsky. So due to the fact that we are using binary arithmetics here, we can very often find some interesting and unexpected ways to improve the speed of the algorithm. Okay, let's go further. Now about groups. I suppose that everybody who is here knows about groups, but let me again formalize definitions that I will be using further. So any, first of all, any finite group can be implemented as the set from 0 to cardinality or order of group -1, together with two-dimensional KD table. This KD table will be represented as a two-dimensional array and one-dimensional array that representing the inversion operation x to x inverse. And in my implementations, the only requirement for this representation is that neutral element should be 0. This is the only, basically, restriction for the implementations. For instance, for cyclic tables, there is obvious representation. Cyclic groups, sorry. For cyclic groups, it is obvious representation because in this case you have 0. It is the 0 of cyclic groups. Operation, it is just arithmetic operation in computers, so it is obvious representation. But for other groups, you just need the KD table to represent this group, and that's all. Okay, subsets and elements of the group in my algorithm will be denoted by capital and small letter, Latin letters respectively. And in computer implementation, there are just bit sets and integers. And I need just a few additional operations that are usually generated by iterative traversing of the specific bit sets. So first of all, I need the multiplications of two subsets of the group, obvious operation. Second, I need the inverse of the subset of the group. It is the set that consists of inverse elements of this subset. And third, it's a square root of the set. It is all elements from the group, which squared belong to this set A. That's basically it. I do not need any more sets, and you see it later. And also, one thing that I need, it is the automorphism group of, currently it is group, but actually of any mathematical structure X. Later, I will show you this mathematical structure X, and it is just a permutation group that can be represented also as two-dimensional array of permutations of X, which are the automorphisms. Okay, Now let's go to the definitions which are needed for my algorithm. So first of all, very important notion, it is a base block. Its definition is very simple, but still it is very, 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 very important and has a lot of properties that I will show later. So we had in the beginning the axiom, first axiom of Euclid, that when you have two different points and you have lines that passes through these points, in this case, it is needed that your how to say that this should be the unique line that comes that passes through these two different points, and this definition is basically the consequence of this requirement. So let's consider this definition that for each G belongs to the group, and for each left shift of this base block, it should have the property that when this shift intersection with block B has more than one points in common, then these blocks should coincide. So what does this mean? That when the action of the group is performed on the base block, it can all the elements in the orbit of this action should not intersect the base block in more than one point. And when it intersect in 2 points, it automatically should be the same as the base block. Okay, so let's go further. Second definition needed, it is for a base block, its difference. Actually, in these definitions, I'm trying to be consistent with a handbook of combinatorial designs. So definitions were not invented by me. I just adapted the definitions from the handbook to my definitions to be consistent. So for base block, its difference is the set of A inverse C for AC belongs to the block B, and A and C are different. So for base block of size K, you can see that the maximum number of differences is K times K minus 1. Okay, next definition, it is also adapted the definition from the handbook. So a base block B is called full if its stabilizer, it is the set of elements from groups that stabilize this block is trivial. Slanted if the cardinality of stabilizer is equal to the cardinality of the block. Or it can be proved that equivalently block is a right coset of some element G, and otherwise it is short. And next we have a lemma. Actually, this is a lemma needed for the algorithms that will be introduced. So let be a base block of group G. Then first property, if group G is abelian, then base block can be only full or slanted. So there are no short blocks. So stabilizer should be either large or trivial. Second, it is about the cardinality of base block. So cardinality of base block can be cardinality of difference of base block can be connected with its stabilizer via such simple and elegant formula. So you just need to multiply cardinality of B times cardinality of B minus 1 and divide by the cardinality of stabilizer. Okay. And as you can see, for instance, for full blocks, cardinality of different set is K times K minus 1. Third property, that intersection of difference of the block with the elements, involutive elements of the group should belong to the stabilizer. So actually, the also consequence of this is that full block cannot have differences that are involutions. And fourth one is that GB stabilizer order divides the cardinality of the base block, and moreover, every base block is a union of some right cosets of GB. Okay. Next, let's go to the difference families. Also, the definition and everything is adapted. So the orbit of base block is a family that consists of left shifts of this base block. And second important lemma is that, first of all, when you have left shift of the base block, difference of left shift of base block and of base block, they are equal. And second, if differences are different, not equal, and when they intersect, then by some specific left shift, you can actually break the first Euclid's axiom. Then in this case, you can apply some left shift to the block B, that it intersects C in more than one point, and these shifts are not equal. So in this case, you will break the Euclid's first axiom. And this lemma that I just introduced shows how to define a difference family. So difference family in a handbook is more general, but my definition of difference family, it is adapted to Steiner to designs. So a family that consists of base blocks is a difference family if disjoint union of difference of these base blocks, it is exactly this group without the neutral element. This is also very nice and important definition that helps to build the algorithms. When we have just some set of base blocks which have disjoint differences, we will call it partial difference family. And because in most of the algorithms we are considering Steiner designs, so we assume that all base blocks of this difference family have cardinality K. Okay, let's go further. And next important lemma that connects difference families with Steiner two designs. For any difference family, obviously with where all blocks have cardinality K, because I told that this structure that consists of, first of all, group, and secondly, the union of orbits of base blocks in this difference family is a Steiner two design. Okay. So very nice lemma that connects these difference families with Steiner two designs. Okay. Next notion that I need, it is a block minimality. This notion is needed for various optimizations of the search algorithm that allows to cut search tree significantly. So first of all, also very simple and straightforward lemma. If a group G is abelian, then difference of block B is equal to difference of inverse block B times -1. And according to this lemma, there are two actually definitions merged into one. So the minimal form of a block B of firstly, let's consider non-abelian group. Of non-abelian group is just the smallest element of its orbit, according to the lexicographical order that we introduced. And when we have abelian case, in this case, it is union of orbits of B and the orbits of B times -1 in the lexicographical order of POG. And we can see that the minimal form of a slanted block is just some specific subgroup of G. Okay. And also one more lemma that helps a lot in the case of cyclic groups, that a full block of a cyclic group is minimal if first element is 0, and two simple arithmetic inequalities should hold. Okay. Next, after introducing base block minimality, we can also introduce the difference family minimality. And first of all, let's introduce one more notion, that a mirror of a family is a family obtained by replacing some blocks by its inverses. Okay, then the minimal form of a difference family in a group G is a smallest element of the family. Let's review this, what we have here in the brackets. So first of all, we consider minimal elements, but for all automorphisms of I'm sorry. Sorry. Okay. So the minimal form of a difference family in a group is the smallest element of this family. So first of all, what we do, we go through all automorphisms of the group, then act with this automorphism of on the base blocks of this difference family, and take the minimal element of minimal form of these blocks. And this minimal form is in the lexicographical order on power set of G in this type. Okay. Now, also one more important lemma from the handbook. So let B be a difference family in a group G. If G is not abelian, then Steiner two designs generated by difference family B and minimal form of difference family B are isomorphic. So according to this, you just need to generate different minimal forms of difference family and families, and you basically by this will cover all possible Steiner designs generated by difference families. So if G is abelian, because we introduced a slightly different minimal form for abelian case, then the Steiner two design, it is my addition to this theorem, then Steiner two designs generated by minimal form of B and some mirror of B are isomorphic. Okay. And third fact, that we can obtain up to 2 times n minus 1 non-isomorphic Steiner two designs from a difference family in abelian group by mirroring. So again, you can generate in abelian group difference families, and then when you have this minimal forms of difference families, you can restore all possible difference families by mirrorings of this difference family, and that's it. Okay.
Can I just sorry? Can I just interrupt for a second?
Yeah. By the way, when you need to ask something, you just interrupt me and ask directly. Yeah.
Well, I wanted to ask something. The second point in this lemma here. Now, I didn't quite understand what you're saying with respect to the sentence just at the bottom. So you say that for any mirror of B, it's going to be, the design is going to be isomorphic to a minimum of D. Or is it like there exists
for some mirror?
For
instance, let's consider Steiner design that consists of 15 points, yes, and 3 points per line. So S2, 3, 15, yeah?
Yeah.
There is only one minimal form of the difference family in the way I introduce it here.
Okay.
And this minimal form corresponds to the projective space of order 2. Okay? This projective space consists of 15 points. But when you, on this minimal form, execute mirror, so you just fix the first block and mirror only the inverse the second base block, and you generate a Steiner design again by this cyclic group consisting of 15 elements. You will obtain the non-isomorphic Steiner design.
Yeah, I think I see now. The thing is, you kind of introduce this rather strong notion of minimal form for a difference family, and in the case of abelian groups, these automorphisms also include just mirroring or taking inverses, right? So, you need to include these operations in order to say they are isomorphic. Okay, sorry for interrupting. I understand now. Yeah.
No, everything is fine. If something is unclear, just ask the question. So when we're generating minimal forms in case of abelian group, we do not cover initially. We do not cover initially all possible Steiner designs, but then to this to these different families, we apply 2 times n-1 mirrorings, and then filter these mirrorings by isomorphism. And in this case, we do obtain the full enumeration of possible Steiner 2 designs generated by different families, but in abelian groups. So in the search stage, when we generate minimal form, it reduces the search tree, but in the end, using mirrorings, we retrieve all possible difference families for abelian groups. That's the basic idea of this mirroring. It helps also to cut search tree a lot. Okay, let's go further. Okay, and how algorithm was developed in the beginning, I just after I understood the example from the book Thinking Geometrically, I tried to reconstruct this difference family, and I just my idea was, okay, let I build this difference family one by one. So first of all, I will add 1 point, then I will think what points are allowed to add to have the second point of the base block, and so on until I build the block. So let's look at these images and try to reproduce my thoughts. So first of all, we can note that we can start always from the zero. Why we can start from the zero? Because we can just rotate this base block so it will intersect zero, and that's basically it. Then second point, assuming that eventually we need to cover all differences, should be 1. Also, obviously, yeah. And as we can see, when we add 2 points 0 and 1, then to have the full blocks. So this is the visual representation how to build full blocks. Let me remind the full blocks. These are blocks with a trivial stability. So because full blocks have only different differences, so in this case, when we added 0 and 1, first of all, immediately 2 and 12 are forbidden. You understand why? Because difference between 2 and 1 equal to difference between 1 and 0, and difference between 1 and 0 equal to difference between 0 and 12. Okay, this is obvious things, but less obvious thing is that when we added 0 and 1, then potentially 2 values are forbidden in cyclic groups. In our case, it is 1, but potentially 2. First of all, it forbids 7. Why? Because difference between 7 and 1 is equals to difference between 0 and 7. And this is less obvious. And when we are tracking only the differences that are currently included, we cannot exclude 7. So this showed me that I need to introduce one more thing, one more set that tracks something, and this set is namely a whitelist. So whitelist, it is just a set that tracks the set of allowed next points in the base block. Okay. So that's it. Now let's assume that as in the example, we just included 4. And when we just included 4, we have one base block 0, 1, 4. And let's start building the second base block. And immediately in this case, you can see that a lot of values are immediately forbidden. Why? Because they repeat the same difference. So between 0 and 3, this is the same difference that with 4 and 1, and so on. So you can see that a lot of differences are already excluded. So let's add the second difference. So the second difference should be second point. Second point should be 2, because difference 2 is not currently covered. So we cover the difference 2. And in this case, due to the rules that I explained before, you can see that how many points are excluded from the whitelist. So after this, only 7 and 8 remain valid. And this is the possibility. So second block can be consisting of 0, 2, and 7. And by this we finish the little bit transformed difference family that was introduced in the book Thinking Geometrically. Okay, this is the basic illustrated idea. And let's go to the next lemma that helped also a lot during the construction of the cyclic difference families. That for cyclic difference families in cyclic group, that one of the following holds. So there are only 2 possibilities. First of all, if V is equivalent to 1 mod k minus 1, and in this case, this difference family should consist of only full blocks. And in the second case, when V is equivalent to k, this difference family B should consist of only one slanted block, which is equal to a subgroup of ZV of order k, and also the full blocks. So this shows that for building difference families in a cyclic group, so we need to know how to build full blocks. And I showed you how to build these full blocks. Okay. And now the description of the algorithm for building full blocks, obviously, because we need to build full blocks. So let's learn how to build full blocks. Okay. So let me have partial difference family, and let delta correspond to the current difference of this difference family. So when we build the new first full block, then first 2 elements of the new base block should be neutral element and minimal element from complement of group G without neutral element with this covered differences. Okay. Also, I told you that we need a whitelist to track, because tracking differences is not enough. And this is our search state. So our search state consists of block B, the current difference family difference, and a whitelist W. And the algorithm consists of 2 principal ingredients. First is the function accept, which calculates according to the state which corresponds to the incomplete block B, next state for the block B union X. And the other part is just a recursive procedure search reporting different values. Okay, and for cyclic groups, a large performance boost of algorithm is achieved using cyclic shifts, which I mentioned, this cyclic shifts can be rewritten using elementary operations, and this really gives a large performance boost. And using arithmetic operations instead of KD table accesses, because we have a canonical representation of cyclic groups using the numbers. And in this case, we just transform from multiplicative notation to additive notation, and just have this operation which is replaced by specific specialized operation on cyclic groups. Okay, now we have everything to introduce the simplest algorithms for building base blocks. Okay, first function is function accept. So function accept is formalized thing that formalizes the pictures that I showed to you. So first of all, we generate new block that consists of a block with added X. Then we have the whitelist copied. Then we have the difference copied, and we iterate through the points in the base block and do some calculations, and you can see that whitelist shrinks 5 times in this case. Yeah, you can see how whitelist shrinks, and actually the shrinking of whitelist, it helps to the speed of the algorithm, because eventually whitelist becomes very small, and you just understand that you do not need to do any operations further. And in the end, you just return updated state that consists of block with added X, updated delta, and updated whitelist. And second is the search. Search is also pretty simple. So first of all, if we build fully the base block, so if the coordinate of base block is equal to k, then we just add this block to our difference family. Then we check the difference. If difference is equal to group G, then we covered all differences. We can report this difference family and exit. In other case, we just introduce new whitelist, which is just the complement to the delta in the beginning of building the base block. Then initiate the base block that consists of, as I mentioned, the neutral element. Then add the minimal element in the whitelist to this base block and execute recursive search. In other case, we just iterate through the whitelist, starting from the maximal element of the block B, and again just accept the point X to the base block, and again run the recursive procedure search. So such simple. But to achieve such simplicity, it took a lot of time, actually. Yeah.
Okay, can I ask again one question?
Yeah. Yeah.
So obviously, a lot of the efficiency of the algorithm comes down to the whitelist and your criteria for shrinking the whitelist.
Yes.
You have these 5 reductions. Can you explain? I'm curious about the ones that include the square root. I guess this is something more general than when in the example you excluded 7. Is this somehow the reason why you can shrink it?
There is a reason. I explained the reason. So first of all, when you are generating everything, so when you are building current block, in this current block, when you already added 0 and 1, yes, you excluding 7. 7 you are excluding because 7 is on the same, how to say, let's say distance from 0 and 1.
Yes. And is
this
this
and
kind of the reason?
in cyclic groups it is half of element, and if you generalize it to the arbitrary group, you need just exclude all elements that are on the same distance from already added points into the block. Incomplete base block, you need to exclude elements that are on the equal distance, and this distance is difference. And if you take a paper and pen and try to understand how to generalize this into the case of any group, you will came to the same formula that is here with square root, because actually the half in the multiplicative case, it is square root.
So this is the first. So this is the one that says you are excluding well times square root of d. Is that correct?
Yes, it is completely correct. It is square root of d, and this square root of d, it is not a single value. This is the reason why d is in brackets, because it is actually square root of set that consists of only d, and this square root, it is a set. It is not a single value, it is a set of values, and this set of values can be 0 values, 1 value, 2 values, 4 values, and so on. It depends on the structure of the group. This
okay,
square
great.
root.
So I think now
square root.
understand.
Let me go back. Square root. It is where I defined it. Here it is. Square root. It is values are in G that squared values are belong to this set A. This is the square root of the set. Yeah. And when you analyze this generalization from the cyclic group to the any arbitrary group, you will just come to the same formula that is here with square root. And in case of cyclic group, it is just divided by 2. Okay.
Okay, thanks.
Yeah. So yeah, and when we have this search and accept functions and procedure defined, we can just now have the full algorithm. And full algorithm is actually very simple. But it is algorithm for specific cases, like for instance for cyclic groups, some abelian groups, and some non-abelian groups. So first of all, if K does not divide order of G, then we to initialize our algorithm just invoke. First of all, generate whitelist that is a whole group without the neutral element, then generate the initial state, then accept minimal element of the whitelist to this state, and execute search with empty incomplete difference family, partial difference family, and this search state. In the second case, in cyclic groups, using again this lemma, we know that there is one subgroup of order K in G, and we do the following invocation. First of all, whitelist in our case, it is this group without this subgroup. Search state consists of the neutral element, this subgroup S and whitelist. Then again, we accept minimal element of the whitelist as a second element, and again execute search, but this time with added subgroup as the slanted block of this difference family. And these two cases cover all difference families in cyclic groups, many abelian groups, and some non-abelian groups. Okay, but this is not, how to say, exhaustive algorithm for general case of arbitrary group. And this example shows it. So let's consider abelian group Z3 times Z3. Then the affine plane of order 3 can be generated by two difference families in this group. First difference family consists of one slanted and one full block. So this is a subgroup And this is a full block where all differences are different. And this way consists of 4 slanted block subgroups. So it's basically, if you know about the Andre theorem of generating translation planes, this is exactly the case that comes from this Andre idea. So here we have only block subgroups, and actually when you're generating difference families that consist only from subgroups, you are just in the Andre theorem for generating translation affine translation planes. Yeah, but these algorithms could be extended to generate mixed cases of full short and slanted blocks, and I will show you how it is achieved. Okay, so let's go to a more general algorithm. So more general algorithm is based on the fact that the number of slanted and short blocks is not very big, and we can pre-generate them. So actually, this is what we are doing. So first of all, we are generating the family of all minimal non-full base blocks. So blocks that are slanted and short. If G is abelian, then this S is very simple. It is just the family of all subgroups of G of order K. In non-abelian case, an algorithm that producing this family will be discussed later. But actually, in the beginning, when I started writing this algorithm, I just generated all possible base blocks and filtered non-minimal and non-full, and it was performant enough. So this how to say, this part is not performance critical, and actually this how you generate it, you can just invent your own algorithm for generating this family, and it will work well. Yeah. Then second part, you are building the graph. That vertices are the elements of this minimal non-full base blocks, and edge has such property that S1, S2 is an edge when differences of S1 and S2 are disjoint. Then what you are doing? You are finding all clicks in this graph such the set. Here you can see it is basically a whitelist. So G without E and without the difference of this click C has two properties. And first property, we are now have arithmetic need, because we know that every full block has k times k minus 1 differences that we require that this whitelist should have k times k minus 1 differences. And second, we should exclude involutive elements by our slanted and short blocks, because full base blocks, as you know, cannot have involutive elements. And this is basically the only two restrictions that are needed for these clicks. Okay, then next part of the algorithm. For each this click, invoke. First of all, generate state that consists of neutral element, then as a difference you take neutral element together with delta, with difference of this click, and whitelist that is introduced here. Then again accept element minimal of whitelist to the state, because we need to cover all differences, and again execute search. And then the theorem by me. This algorithm generates all possible difference families for any group G. For cyclic and some other groups, and it consumes very small, it is O big from just the order of G squared amount of memory. So it is not only the fast but very memory effective algorithm, if you do not need to generate all these clicks. But maybe with clicks, it also has not a larger amount of memory, but I did not test it. So generally, it really consumes very small amount of memory. Okay. Now let's talk about the optimizations and improvements. And this is the reason why I introduced the automorphism group in the beginning, minimal form, and so on. Because in other case, you just will consume a lot of time. Just by generating non-minimal difference families, and in the end, the Steiner designs that you are obtaining from them are anyway isomorphic. So first of all, nowadays most of PC are multi-core, so parallelization is simple and effective way to speed up algorithms. So instead of running search from the very beginning, it's still possible to store some initial states into a file and then read this file and process cases parallelly one by one. This idea was motivated by blackouts that started happening after Russian shelling, and they target our power stations, and after it you just launched your calculation and oops, blackout started and you lost all your progress. So, but it actually helped, first of all, to parallelize this algorithm, and secondly, to perform it in, how to say, stages. And usually you generate a large file, like few megabytes of states that are stored into the file, and then you start processing them, and you can stop your algorithm at some point. You can just parallelize it. You can do even more stages and so on. So for abelian groups, usually the first full block in minimal form of first full block is stored. In other cases, you can store a minimal form of initial clicks. And this also is a point of optimization. Yeah. So also another optimization is of the minimal form. So for abelian group, you can just filter out some difference families by the minimality, and in the end you restore them by mirrorings that were introduced. And also, since abelian non-cyclic groups have much larger automorphism groups, so in case of cyclic groups, the amount of initial states is usually very large, but it achieves a lot of performance improvements because of it maps very well on the arithmetic operations of the computers. But for non-cyclic abelian groups, usually these groups have very large automorphism groups. So it is strange, but running times for all abelian groups are comparable. So they do not differ very much. And for a cyclic group, we can cut search tree significantly by running only over elements. This is the consequence of lemma I introduced. So this also very large improvement. I will not explain it, but you can believe me that it cuts search tree also very significantly and allows you to analyze all cases and skipping the cases that will definitely not lead to the difference family. Okay, now about the results. So first of all, after the contact with Bycheva and Topalova, we had a paper that was released just a few months ago, or even months ago. Yeah, months ago, I suppose. Yeah, about one more extension of the enumerations for cyclic difference families. So we reached boundaries, I suppose, for current PCs in this paper. Second paper, it's about point transitive Steiner systems with such parameters. And I will introduce one of the results of this paper to you here. And it connects basically my results to Zvonimir Yanko, who is famous Croatian mathematic and how to say, and one of the sporadic groups is named after his name. So I'm very proud that I can somehow be related to this famous mathematician. So in 1998, Janko and Tonchev introduced first Steiner design with parameters 7 points per line and 175 points in total, with automorphism group of order 4200. Then Vedran also find out one more. I don't know how it was obtained from this design, but I suppose it was obtained from this design. And in 2025, I found one more design, which is actually very related to this design, because this design can be presented in a form of a difference family. And it is a difference family of abelian group. This group is Z7 times Z5 times Z5. And when you perform mirrorings to this design, to Janko Tonchev design, you actually obtain all three designs. So for me, it was very strange that Janko Vedran did not notice this simple thing. Yeah, and this was the third design that was found. And third theorem, it is non-trivial. It also requires to do full search for the cyclic groups, cyclic group Z175, and we have the theorem followed by exhaustive search that there are exactly 3-point transitive such designs, and there can be no more. Okay. Second part, I suppose that I have some time, and when I finish this part, this will be the logical split in the algorithms. So currently, today I will explain only the algorithms related to the groups. Yeah, so there is a definition in a handbook. So in handbook, there was analyzed a lot one rotational designs. These designs were introduced by Rosa and Phelps in early 80s. But at that time, they considered only the cyclic groups, and in handbook, there is a generalization which I will be used, and even generalized more for the Steiner 2 designs. Only for Steiner designs, because this handbook definition, it is related to BBD, and my generalization cannot be, I suppose, used for it, but nevertheless. So one rotational designs, it is just very simple, similar in Steiner case for the very similar to the difference families, but we have the structure that, first of all, to the group we are adding infinity and converting this group to a semi-group. And we require for this difference family to be union of G together with this infinity. So, first of all, observation. In this case, about this one rotational designs, and when we correspond this one rotational designs to the difference families, one of the base blocks should be in the form B infinity and this infinity, only one block. And this will basically consume all required differences with infinity. And other blocks are just regular blocks. So this simple observation led me to the following generalization. So this generalization is F fixed difference families and F fixed designs. So let G be a group and F be a number such that this divisibility condition holds. And as you can see, the divisibility conditions, it is conditions for an existence, necessary conditions for existence of Steiner 2 designs, basically, with F points. And a family of base blocks, first of all, we have some t number of regular base blocks of length k and exactly f base blocks of cardinality k minus 1 is a difference family, and this is the explanation. When each block has cardinality k, each block bi, and each block bj infinity is a subgroup of order k minus 1 in G. And initially I had, how to say, only the algorithm for one rotational. Actually, this generalization came later. But what motivated me to study this one rotational designs? The very simple theorem that was proved by Marco Buratti in 2001, and Marco stated that there exists unique non-isomorphic one rotational design. And when I tried to reproduce this theorem, I accidentally found that it is not unique. Actually, there are 7 non-isomorphic one rotational designs. And you can see the number. The number of points is 25. It is very low, and only in this, how to say, in this small amount of points, there is, how to say, not verified well result. And according to this, I thought, okay, in this case, maybe I can do this verifications. I can reproduce all cases that are introduced, and actually this one rotational designs and f-fixed designs eventually became very profiling. Yeah. Okay. So now let's generalize our previous algorithm for f-fixed designs. And actually this generalization is very simple. So I marked blue only the difference between the general algorithm for the group and the algorithm for generating f-fixed design. So as previously we generated the family S of all minimals, but currently we have short blocks of cardinality k and slanted blocks of cardinality k and k minus 1. Then again, we build the same graph. We again find all cliques, but currently this set should have 3 properties instead of 2. First properties are the same. So first of all, to have full blocks, we should have that in white list there should be only k times k minus 1 differences. Secondly, we should exclude all involutive elements from our whitelist. And third is that number of blocks of cardinality k minus 1 in this clique should be equal to f, because we have f infinity points here. And again, for each C, invoke exactly the same initialization procedure. And in the end, to recover the Steiner design, we attach every bj infinity block of size k minus 1, because we need to extend it to k points, to a generated f-fixed difference family of a generated f-fixed family to a point of some known as 2kf design. And in this case, we produce Steiner design that has k points and per line and this number, so order of the group plus f design. And as you can see that for f, this is more than k, the number of isomorphic designs grows very quickly. Why? Because we can just do some permutation of this Steiner design that is attached. And this permutation will give you non-isomorphic Steiner design. And according to this, I'm raising the following problem. Estimate the number of non-isomorphic f-fixed Steiner designs. For instance, for arbitrary group, not for general group, but for arbitrary group. Okay. Again, more results that occurred. after it. So first of all, after finding the issue in Burati's paper, I did enumerations of one rotational Steiner systems for a lot of different parameters. Secondly, a lot of point transitive and one rotational unitiles of order 5 was generated. At that point, in handbook, there is only 2 unitiles of order 5. And there is a paper of Stoichev and Gezek. They found unitals that are included into the projective planes of order 25. Yeah, but these unitals are mostly distinct from my unitals because these unitals have very small automorphism groups, and point transitive and one rotational unitals have large automorphism groups. And third paper that was kind of extended, it was also paper of I don't know whether people are present. Vedran at least is present. So Vedran generated a lot of unitals of order 65. And there were one rotational unitals of that had orbits of 1 point and 64 points. And I read this paper, I analyzed the unitals, and I found that this, in case of one rotationalness, it is not complete. And in this paper, there was 67 unitals with automorphism group of order 64 and 8 unitals of order automorphism group of order 192. And actually, I found a lot of new unitals, so you can see it here and here that extend these tables. And to introduce the next part that will happen next week, the examples that motivated following the generalization. So after developing these algorithms, I tried to reproduce Hermitian unital of order 3 and reunital of order 3. It is well known that they have point transitive automorphism groups, but we cannot generate them using any difference families of any group of order 28. I shared it with my colleagues who are present here. It is Taras and Alex. Such problem. This problem is already solved. So is there a way to generate unitals about using something similar to the difference families? And there was suggestion from Taras that you can generate them using G spaces. And this is how to say ending point of my presentation for today. And that's it for now. Thank you for attention of the first part of the algorithms.
Thanks, Ivan, for a very nice talk. Yeah, I guess obviously I do have some questions. Yeah, but I would first ask people from the audience, because the last seminar on Monday, I just went ahead and asked, are there any people who would like to ask some questions before I do? Okay, if not, then yeah, let me just start by saying that Mario Pavcevic is present. Anna-Marie Nakic is unfortunately not. Oh, okay. Does someone want to ask a question?
Yeah, I want to ask a question.
Okay, please go ahead.
I want to ask about the number 18. It's your theorem about abelian groups, about estimation of your code. 18.
18, okay. Here, yeah.
Here you write for cyclic group and some other groups. What you mean for some other groups? It's abelian group that is not cyclic, or about some non-abelian groups? What does it mean, some other groups?
Some other groups means a lot of abelian groups. You can use these algorithms. So these cases, some groups are explained earlier. So it is here. For abelian groups, it is a groups where there is only one subgroup S of order K in these abelian groups. It is first type of groups, and second type of groups, it is if K does not divide G. In this case, using this algorithm, we are generating only full blocks, and this algorithm is applicable. And also some non-abelian groups, for instance, obviously when order of non-abelian group divides K, and in this case it is more complex. It is not only one subgroup, there are different things, but again, this covers a lot of abelian and some non-abelian groups. The example is basically this. So this design, it is generated not by cyclic group, it is generated by group Z7 times Z5 times Z5. It is not cyclic group, but but it actually is the case of this theorem. So for this group, it is also applicable, and also in this case, it consumes O big from square order from the group. Yeah.
And I think that it be more understandable maybe for readers if this plan to be published to or explain more in a statement of theorem what is mean about these two cases of this K and so on, or formulated previous two lemmas about these situations, and then formulate that we describe in these two cases, we describe that our consumes and so on. But I think that for some other groups, it means that non-abelian maybe some metacyclic groups, yeah?
Yeah.
Mm-hmm. It's like,
Yeah,
no, I don't know whether...
Answering your question, I am currently preparing a paper which will be published in arXiv soon, and in this paper, this some other groups is explained. So
yeah. Mm-hmm.
in I don't know, week or two, I will publish it on arXiv, and you will be able to see what exactly are the some groups. But I just added this. This is not. I understand this is not a strict formulation of the theorem, because some other groups it is not strict. But I just simplified it for the presentation, because I do not have time to explain what types of groups are applicable for this case for a small amount of memory. Yeah. So sorry for this.
But it's a really very good estimate. But and another question about parallelization. I understand that you use parallelization in your code.
Yes, I use it very widely, almost in every algorithm.
What is the maybe in the beginning of your talk you tell, but I realized some problem with the connection, and that's why I really don't know what language you use, what system you use for realization. No, I mean a computer.
In the beginning, I told that I spent 10 years in IT as Java developer. Due to this fact, I have my own repository. This repository is in the very end of my presentation. You can check it on the GitHub, and it contains all code. Yeah, here it is.
Thank you.
So you can Google. My nickname is Hetman. You can Google this repository, matutils, and actually this is not very structured repository. So I warned you. This is not. This is not a, how to say. This is not a factory, but it is more like laboratory. So it is a place where you experiment and so on. So, for instance, algorithms that are explained, they have their strange names. Name it is BE finder test, something like this. And there are different variations of these algorithms. But yeah, so some of them can be run even without preparation, but some require understanding what I'm doing and some preparation. before be able to reproduce. Yeah, so my code is in Java. Until the 2026, I even did not use any other libraries, but with thanks with help of Vedran, now I have integration with Naughty, which is a simple automorphism group, because I had my own copy of Naughty. It was slow, and thanks to Vedran, I have now very fast automorphism checker. So it is the only dependency from my code on Naughty, and yeah.
What about gap? Why you don't use gap? Because really, I understand that the Kelly table it's more easily for realization for group, but in a gap you really have a very huge library of groups. And
yeah, thank you for this question. So about gap. I'm using gap, but not as a dependency, but as a standalone system. So how I use gap? So I'm launching gap, generate a KD table by gap of specific group, and then just use this KD table. So
I understand this. That's why
yeah,
I asked you.
this is the only how to say thing that I need from gap, because gap is a large database of groups, but from gap I need only KD tables. I don't need anything else, and this is the reason why gap is used, but in a very limited way in my algorithms.
Okay, thank you. But no, maybe next time we have other question. But thank you very much. Interesting.
Thanks, Elena, for your questions. Okay, one short question about F-fixed difference families and designs. So this is basically your definition, right? This is a generalization of one rotation which have been very well studied.
Yes.
And did you find any interesting examples, for example, for two fixed, for small, when F is large, you said you can, there are many
is impossible because we need the divisibility conditions.
Okay, so the smallest possible would be where you have
smallest possible, which is
one,
not
right?
one rotational. It is K fixed in this case.
K fixed.
And about K fixed, you already observed this K fixed. This K fixed, they are in my paper about more Steiner 27175.
Okay,
this additional, they are actually F7 fixed, and I found them also. When you go further and you just have F more than K, in this case you have just explosion of the different Steiner designs, and actually this is the reason why after some point enumerations become just how to say, not needed, because you just physically cannot store this amount of designs, and there is a lot basically of designs that can be fixed, and I have examples for a lot of Fs and Ks. So yeah, actually there is a very nice and large source of designs, this F fixed, and for me it is very strange that they were also not studied for some reason. They actually were studied, but they were studied for BD, and the lambda was more than 1. But for lambda is equal to 1, in handbook, for instance, there is even no example of such F-fixed designs, but there is a lot of them, actually. And yeah, there are F-fixed unitals, which led to the discovery of one undecided case from handbook, actually. After introducing this F-fixed, I solved one undecided case, because I just started by the I started generating this F-fixed for more and more, and in the end, wow, I solved an undecided case, and it is a fixed design. Wow.
But I suppose that the most interesting case would be then with f equals to k, right? After k.
Yeah,
F
the most
equals to 1.
one rotational are extensively studied, so we know a lot of them. But for f equals k, yeah, there are also a lot of interesting examples, and these examples I uploaded it to our future Zenodo archive, and yeah, there is a lot of them.
Well, one more thing, this is what I wanted to hear. So this is a very interesting definition in the sense that it really gives some new examples. The reason why you kind of with your programs got stuck with these unitals of order 3, the classical one and the reunital, which have transitive groups, but you can't generate them from difference families because they don't have sharply transitive subgroups.
I know.
And
I know this.
This is kind of one of implicit assumption of yours when you define base blocks the way you do, is that you have a bijection between the points and the group elements. And this is possible when you have sharply transitive action.
Yes.
So
Yes.
these unitals, they don't have sharply transitive subgroups, and you simply cannot identify them with group elements. The points you cannot identify, and this is kind of one assumption you're making when you're searching for Steiner designs with difference.
Yeah, I know this, and but in the beginning, for me, it was not clear because I told you that we are learning the finite geometries, how to say, step by step, and at that point, for me, it was strange why it is. Then I shared this observation with my colleagues. Taras explained to me why. Exactly the same you told right now, exactly the same Taras told me. And but it had a positive consequence that more general algorithm was developed according to it. And yeah, so I understand that some questions can be, I'm a proponent of the think that there are no stupid questions. Question becomes stupid if person ask these questions 3 or more times, because it means that the person just do not understand the answer. But when you ask one time, whatever the simple question is, it can actually lead to something. You can realize something. You can share something with your colleague and so on. So do not afraid to ask questions and do not afraid to look dumb. You will look dumb when you ask the same questions 3 or more times. This is the point where I agree that you look dumb. But in other case, you can ask anything, even question the basics of mathematics. And if you have the right form of the question, it can lead to some interesting consequences. Yeah.
Thanks again for a very nice talk. Let me just remind everyone that this is the first part. The next part is going to be 1 week from now. There's going to be an announcement again. And let me just shortly advertise on Monday, the 2nd of March, there will be a talk by myself in the Lviv Seminar for Geometry. So this will be obviously connected to Ivan's talk, a little bit from a different perspective, because Ivan is kind of going from the more special way to construct designs to more general, and my talk will be kind of top down, not bottom up. But anyway, I will send, Taras, I suppose, already sent an announcement to people from Ukraine. I will send his announcement also to the participants of today's seminar from Croatia. So if anyone will join the Lviv seminar for geometry, he will have the opportunity. Okay, thanks, Ivan, again, and see you on Monday and see you a week from now with the second part of your talk.
Okay, thank you.
Thank you, everyone, for participating. I will now cut off seminar. I have to go somewhere. I'm a bit of a hurry, so after I have time, I will send you the video. Now I better stop the video now. The recording. Okay.
See you in a week.
Yes.
Okay,
See you.
Thank you so much for everything. Thank you.
Okay. See you
I will
soon.
send you announcement. Yeah.